Hi everybody. We're doing statics problem solving. Our topic, three-dimensional force systems. Our question, the force F in the figure is perpendicular to the ABC plane. Find the Cartesian components of the force F. A, B, C, and F are known values. Yes, we have a tetrahedron. There is a force F acting perpendicularly on its ABC surface. We are asked to write this force in terms of its rectangular components. We are asked to find x, y, and z components of F. To find these unknowns, let's use the following formulas. X component of F equals F multiplied by L, y component of F equals F multiplied by M, z component of F equals F multiplied by N. So, L, M, and N are the direction cosines. F is given. If we find the direction cosines, we will have found the values we are looking for. So let's find the direction cosines. To find the direction cosines, if we find the unit vector in the same direction as F, we will have found the direction cosines. Because the cosines of the direction are the components of the unit vector in the same direction as the vector F. Let's find u. We need to find u. The vector F is perpendicular to the ABC plane. Therefore, u is also perpendicular. We can find u using cross product. If we obtain a vector perpendicular to the ABC plane, we can find the vector u by dividing this vector by its own magnitude. If we perform the cross product of any two vectors in the ABC plane, we obtain a vector perpendicular to the ABC plane. But in which direction is this vector? It could be in the direction of F, or it could be in the opposite direction. We need a vector in the same direction as F. There are many possibilities. We can choose any one of these possibilities. For example, we can multiply AB and AC. We can multiply BC and BA. But if we multiply AB and CA, we get a vector in the opposite direction to F. We shouldn't do that. Now let's take AB and AC. When we multiply the AB vector by the AC vector using a cross product, we obtain a vector perpendicular to the ABC plane. When we ratio this vector to its magnitude, we obtain the unit vector in that direction. That is, we obtain the unit vector we are looking for. So let's write AB and AC. For the AB vector, we go from A to B. Starting from A, let's write the AB vector by looking at how far and in which direction we go parallel to the axis. We go a distance as far as A, parallel to x in the negative direction, and a distance as far as B, parallel to y in the positive direction. We reach point B without needing to go parallel to z. Therefore, AB equals minus AI plus BJ. Let's write the AC vector. Similarly, we get AC equals minus AI plus CK. The AB vector has no z component, and the AC vector has no y component. Now we will perform the cross product of these two vectors. We can do this in two ways. We can distribute the parentheses, or we can do it using the determinant. Let's try both methods as an example. Multiplying I by I gives nothing. Multiplying I by k gives minus j. How do we see this? We see it in the circle on the right. When we rotate counterclockwise, we rotate in the positive direction. When finding the product of I and k, since we go from I to k in the negative direction, the result is negative j. The coefficient of j is the product of minus a and c. There is a minus sign in front of j. The minuses cancel each other out. The coefficient becomes ac. So the result is ac multiplied by j. Let's move on to the next term. J multiplied by I. J multiplied by I is found as minus k from the diagram. The product of the coefficients is b multiplied by minus a. The minuses cancel each other out again. We are left with ab multiplied by k. The last term is the product of j and k. The product of j and k gives I. Its coefficient is b multiplied by c. So the term we obtain is bc multiplied by I. Yes. Thus, we have performed the cross product. Now let's do it using the determinant. When performing the cross product of any two vectors, when finding it using the determinant, we write the vectors ijk, which are unit vectors, in the first row. In the second row, we write the rectangular components of the first vector p. In the last row, we write the rectangular components of the last vector q and expand the determinant. We can expand the determinant in different ways, but I prefer to expand it in the way shown in the figure. I write the first two columns of the determinant on the right side and create the diagonals. I subtract the values above and add the values below. I reach the result by multiplying the terms on these diagonals. We have vectors AB and AC. We will multiply them with the cross product. We write ijk in the first row. On the second line, we write the rectangular components of the AB vector, so the minus a, b, and 0 terms. In the last row, we write the rectangular components of the AC vector, so the terms minus a, 0, and c. We write the first two columns to the right of the determinant and multiply the terms on the diagonals. We will subtract the terms above. The terms above already have negatives. Since we are subtracting, we put a negative sign in front of them. Therefore, the negatives cancel each other out, resulting in a positive. One of the terms above is AB multiplied by k, and the other is AC multiplied by j. The term below is BC multiplied by I. We will add these together. All three terms are positive. We obtain the same result as before. Now let's look at what we get as a result of a cross product. The magnitude of the vector we obtain as a result of the cross product is equal to the area of the parallelogram in the figure. The magnitude of the vector we obtain as a result of the cross product can be found as the magnitude of the first multiplied by the magnitude of the second multiplied by the sine of the angle between them. We learn this. We see from the figure that AC multiplied by the sine theta is the height. Therefore, the base multiplied by the height gives the area of this parallelogram. We previously obtained the cross product of AB and AC. Let's call this A. Let's call the area of the parallelogram in the figure A. Now we see that the area of triangle ABC is equal to half the area of this parallelogram. That is, it is equal to half of the value of A we obtained. The area of triangle ABC is equal to A divided by 2. We can see this from the figure. Yes, if we substitute these values, we now obtain the vector u. The coefficient of I is BC divided by A, the coefficient of J is AC divided by A, and the coefficient of K is AB divided by A. All three are the cosines of the direction L, M, and N. After finding the cosines of the direction, we can now find the x, y, and z components of the force F. But before we move on to finding them, let's examine these results a little. Now let's look at the figure. We saw that the area of triangle ABC is equal to A divided by 2. The area of triangle OAB is also equal to AB divided by 2. We see this from the figure. After finding these, let's return to the vector u. Let's look at the coefficient of k in the vector u. What is the coefficient of k? It is equal to AB divided by A, which is the ratio of the area of triangle OAB to the area of triangle ABC. It is equal to the cosine of the angle it makes with the z-axis. If we isolate triangle OAB from this equality, we find that triangle OAB is equal to the product of triangle ABC and cosine theta z. What does this result mean? Let's see. We can say that triangle OAB is the projection of triangle ABC onto the plane perpendicular to the z-axis, as we see. Because we find triangle OAB by multiplying triangle ABC by the cosine of the angle between it and triangle OAB. We know that we can find the projection of any line segment onto any direction by multiplying it by the cosine of the angle between them. It's similar here. We obtain triangle OAB by multiplying triangle ABC by the cosine of the angle between them, and we find its projection. We know that the angle that the force F makes with the z-axis is theta z. We see from the figure that this angle is also equal to the angle between the two triangles. The two angles in the figure are two angles with opposite sides perpendicular to each other. Both of these are equal to theta z. Similarly, triangle OBC is the projection of triangle ABC onto the plane perpendicular to the x-axis. The angle between them is equal to theta x, the angle that the force F makes with the x-axis. Again, similarly, triangle OAC is the projection of triangle ABC onto the plane perpendicular to the y-axis. The angle between them is theta y, the angle that the force F makes with the y-axis. Yes, by substituting the results we found, we obtain x, y, z components of F. We obtain the result, x component of F equals F multiplied by BC divided by A. Y component of F equals F multiplied by AC divided by A. Z component of F equals F multiplied by AB divided by A. Here, A is the area of the parallelogram. It is twice the area of the triangle. It is twice the area of triangle ABC. We have given that below. Now let's examine these results a little more closely. For example, if the values of ABC are all equal, what result do we get? Let's write A in all the places where we see B and C. Then, we get x component of F equals F divided by square root of 3, y component of F equals F divided by square root of 3, z component of F equals F divided by square root of 3. All the cosines of the direction are equal to each other. The angles they make with the axes are all equal to each other. Therefore, the rectangular components are also equal to each other. Another possibility, A, could be 0. If A equals 0, if we write 0 where we see A, we see that y and z components of F will be 0, and only x component of F will remain, according to the relations we obtained. When only x component of F remains, then F equals x component of F. If B is 0, only y component of F remains. X and z components of F become 0. Then F equals y component of F. This time F becomes a force parallel to y. If C is 0, this time F becomes a force parallel to z. Only the z component remains. The x and y components do not exist. Goodbye.